Hey guys, hope you are doing well. I'm going to be doing questions 37 to 40 on the General Maths Exam 1. Today, my name is Marshall. I scored a raw 50, but these solutions are not suggested by VCAA or anything. If I do make mistakes, please let me know in the comment section below. But yeah, I'll be putting this video down in a few days, so watch it before exam 2, but I'll put it back up again in a few months.
Alright, so with question 37, there's just two main things. It's that the lookout is 34 meters, and all of our multiple choice answers, they will add up to 16. So that means the pathway cannot include x and then y, because that's going to be more than 34. So we have to find an alternate pathway that gives us 34, which can just be 10, 11, 8y. So 10 plus 11 plus 8 is 29. So therefore 29 plus y equals 34, which means y would have to be 5. And the only option that has y equals 5 is this. And yeah, x, it actually doesn't matter what x is, because it's just saying the shortest path from this to this is that. So your answer is going to be D. Alright, so for question 38, we have a connected graph with 6 vertices, 6 edges. How many of these statements will always be true? So what I would like to do is always just draw a graph. 1, 2, 3, 4, 5, 6. So these are our 6 vertices, and it has to have 6 edges. So it can be like 1, 2, 3, 4, 5, 6. It doesn't really matter as long as it's connected. Let's see if it satisfies each of these 4 conditions. The graph has no vertices of odd degree. And it says which one has to always be true. Well, in this case, it is not always true because this is false. This is 1 degree. So this statement is false. What's the next statement? The graph contains a Eulerian trail. A Eulerian trail has to have either 2 vertices of odd degree or 0 vertices of odd degree. And it has to touch all the edges. So obviously it can do that trail. And so that is correct. Now, if you have a different arrangement, let's say it goes like this. This is both a Eulerian trail and a Eulerian circuit in one. And because if you look in the Cambridge textbook, a Eulerian trail exists only if the graph has exactly 2 odd vertices or 0 odd vertices. So that is also true. The graph contains a Hamiltonian path. Again, Hamiltonian path means that it visits all the vertices, which it is doing right now. And even if we try some weird arrangement, so 1, 2, 3, 4, 5, 6. And remember, it doesn't say it has to be planar, but whatever. Again, it will work. 1, 2, 3, 4, 5, 6. Let's just test it out. 1, 2, 3. Wait. 1, 2, 3, 4, 5, 6. Okay, yep. So that's also a Hamiltonian path exists for here. So this is also always true. The sum of the degrees of the vertices is 12. Well, obviously, the number of edges multiplied by 2 will always be your sum of the degrees. So if you have any graph and there's like, okay, there's like 8 edges, then therefore there's going to be a 16 sum of the degree. The sum of the degree is twice the number of edges, so this is always true. So therefore there are 3 correct statements, and the option should be C. I'm also going to test out a loop and just see if it works. So we'll do a loop here, and then so that's 1, 2, 3, 4, 5, and then we can't make another loop because it has to be connected. Does this satisfy all the conditions? Well, there's a Eulerian trail, there is a Hamiltonian path, and the sum does in fact 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yep. So this, yep. Even with a weird graphs like this, it still satisfies the conditions. All right, so we have a traditional Hungarian algorithm type question. So we have these workers in the table, and then we have they're too slow apparently. So we have Edgar, who's going to complete one of the tasks. And this is his completion time, 9, 5, 14, 8. And then we're going to find out how much is the initial allocation being reduced by. So we've got to find out the first initial allocation, which can be done through your traditional Hungarian algorithm. So let's start with red. So we're going to do our row reductions. So the lowest number is 8. So let's just reduce everything by 8 in the top row. So 4, 0, 8, 1. And then the next one is 7. So 3, 0, 8, 3. And all of these are all reduced by 10 because both Kali and Dexter, their lowest is a 10. So we can essentially reduce everything by 10. So this is a 1, 0, 0, 4, 8, 6, 2, 1. Okay, now let's do our column reductions. And then okay, so let's go to column reduction. So these things can all be reduced by 6. So this is going to be 2, 2, 2, 0, 2, 2, 2, 0. And this can all be reduced by 1. So 0, 2, 1, 0. Okay, let's put over our lines, our Hungarian lines over. So we have 1, I'll make it bigger lines. Okay, so we have 1, 2, and then only 3. So we're going to have to add in additional zeros. So the things that are not covered, the lowest number is this 1. So we can reduce everything by 1 that's outside. So this is going to become 3, 2, 0. And then this is going to be 1, 1, 1. 1, 1, 1. Okay, and then we have to also add everything that is being covered twice, and we have to add 1. So this is now 1. Okay. Now there's new zeros, so we will have to redo the lines. Okay. So to cover all the zeros, we put 1 here. Put 1 here. Okay, so it looks like we are covering all the lines. So 4 lines, 4 tasks, 4 people. That's a good sign. So let's do our allocations. So right now we know that we want the lowest possible. So Blake, the lowest thing that he has is task 2. So he's guaranteed to do task 2, which means that no one else can do task 2. So therefore, that means Kali is forced to do task 1 for minimum time. And that means Dexter, that means Anush's task, her lowest task is this one right here. And then Dexter will be doing task 3. So this is our minimum allocations. So now we have Edgar, and he has 9, 5, 14, 8. So he's going to swap out one of these people. So I'll just remove all of these numbers here just to make things a bit easier to look at. Okay, so now that Edgar's here, he's going to reduce one of these. So he is 9, 5, 14, 8. So initially, he could reduce, so 9, 5, 14, 8. So he could reduce task 4 by 1. He could reduce task 3, task 2, task 1, all by 2. So he can reduce things by 2. But let's not do task 4. Let's make him reduce... well, as we know, Blake is already the lowest thing he can do is already this one. Kali, the lowest task 1 can be done by Blake. Blake 1 has the potential to do task 1 as fast as he can, and same as Dexter. So I would actually we could actually just make Edgar do task 3. So let's make Edgar do task 3. And therefore, we're going to make Dexter do task 1. And then we're going to remove Kali altogether from the system. And this should give us our new allocations. So this is a reduction by 2. And then we went from 11 and we're going to 10. So this is a reduction by 1. So this reduction overall is -3. So we can reduce everything, like the whole overall, by 3 hours. So our answer is going to be C. Shout out to my guy Sharon for realizing that observation right here. Because the thing is, when you reallocate, you can still reallocate more people to be more efficient. Okay, so now let's move on to question 40. We have 15 activities, A to O, that need to be completed. and the activities are not labeled, unfortunately. And we have to find out which activity table works for this diagram. And what I will do at the start for this question is look through it by eye, like your eyesight, and tell which option is wrong. But unfortunately, all of these are really similar because they have two activities that have four predecessors, and then four activities that have no predecessors, which is actually correct because there are four activities that have no predecessors, and then there's an activity here that has four predecessors, activity that has four predecessors. So what I would actually do is create my own. If I was to do it, I would create my own activity table. So let's go ahead and do that. But instead of using the variables A to O, let's do 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then what I would do is label all of these activities with this new scheme. So it doesn't really matter because we're just doing it for ourselves. 1, 2, 3, 4, 5, 6, 7. We got 7, 8, 9, 10, 11, 12, 13, 14, 15. And don't get confused and say, oh, this is the length of the path. This is just the name of the activities that I've decided to put in, just to make it easier, because I don't want to use A, B, C, D, all that, to get us confused. Okay, so now what we're going to do is make some observations. So 14 has four predecessors, and 9 also has four predecessors. So we're going to write down these predecessors. So 14's predecessors is 13, 11, 9, 8. 13, 11, 9, 8. So 13, 11, 9, 8. And 9's predecessors is 10, 3, 6, 7. So 10, 3, 6, 7. So what we actually can make a realization is that these two are connected. So let's use another color. Actually, what we can do is finish our table. So let's just finish our table. 8 is being predecessed by 5. So 5. 5 is being predecessed by 1. 5 is 1. 1, 2, 3, 4 have nothing. 1, 2, 3, 4 have nothing. 1, 2, 3, 4. Okay. So 1, 2, 3, 4 have nothing. We'll just circle it just to make sure we are ticking the boxes. 10, 11, 12 all start with 4. All are predecessed by 4. So 10, 11, 12. 4, 4, 4. So let's circle these. And then 13 and 15 begin with 12. So 13 and 15 begin with 12. 12. 12. And now 6, 7 are remaining. So 7 is 5. So 7 is 5. 6 is 2. 6 is 2. Okay, so let's make some observations real quick. The one that's being... We'll use red color for interesting observations. So there's a commonality, which is 9. And this is being pushed right here. So what this is basically saying is that your 14 is being predecessed by a 9, which is being predecessed by 4 other things. Right? So if we make this connection with all of our options, this can eliminate some things, but unfortunately all of them do have that connection. Now, are there any other similarities between 9 and 14? There's nothing else really. So 9, 10, 3, 6, 7, 14, 13, 11, 9, 8. Nothing else is really connecting 9 and 14 together apart from this 9, 9. Now, what else can we see that is pretty interesting about the graph? Well, 9 is being connected to 10, 3, 6, 7. And if we look, 3 is connected to nothing. So what I'm going to write on top of 3 is no, because there's no predecessors for 3. Now 10, 6, 7. 10, 6, 7, they all have predecessors. 13, 11, 9, 8. 13, 11, 9. Okay, so this is the observation we've made so far that we can use to try separate A, B, C, D and not have to do trial and error consistently. So let's go into option A. Is there something that connects G and N together? Well, yes, there is, because G is being connected right here. And now, what do we also know? We know that in the connection, one of these connections will have nothing, like here. So one of these options here will have nothing. So E, F, C, H, one of these will have nothing. So as we can see, C has nothing. So we can just write no. And then E, F, H, E, F, H, because I'm looking at E, F, H. Okay, so far A is looking good. A is looking good, but it may not be the final answer. Now let's go here. Is there a connection between F and K, the 4 things? In fact, there is K and K. Now, as we see, the one that's being connected to is connected to something that has nothing. So one of these has to have nothing. So E, G, H, J. E, G, H, J. H has nothing, so that's right, no on top of H. No. So these 2 options, A and B, are looking pretty good. Now, let's see here. F and K. There is a connection right here. And now we have to see that there's a pattern where this part, one of them is nothing. So one of these has to be connected to nothing. So is D, okay, D, G, H, J, okay. D is connected to nothing, so let's write nothing. G is connected to D. H is connected to nothing. H, okay. So this is an irregularity. So therefore, C is not it. Now D. There's a connection, which I can see right here. Okay. Well, there's actually 2 connections. There's actually a connection here as well. That is another irregularity, which means we can remove D altogether. And that means we're just going to be left with A and B. So let's see what we can do to differentiate between A and B. So if we look at it through this perspective, let's look through the lens of A. Let's look through the lens of A. So in the lens of A, this is G, and this is N, because this is corresponding to this. So this is 9 is G, 14 is N. Now, what do we also know about? Are there any other things that we can observe? 10, 3, 6, 7. Okay, so we know 3 is special. 6. Okay. So let's have a look at this 6. So what is 6 connected to? 6 is connected to 2. 6 is connected to 2. So I'll just write 2. And then 2 is connected to nothing. No. Okay. So let's see if we can find something similar in here. So E, F, H. Let's try E. So E is connected to A. So let's write A. And then A is connected to nothing. Okay, A is connected to nothing. So I think I can just write no on top. Yeah, okay, no. So it's looking good so far. It's matching this. We'll do another test real quick. 7 is being connected to 5. And then 5 is being connected to 1. And then 1 is being connected to nothing. So I'll just write no. Honestly, I could just write 0, but whatever. So is this... Okay, 7. Okay, let's try F. I will try H actually. Okay, so H is being connected to D. And then D is being connected to nothing. Okay, let's try this last one. Wait, this does not match 7, but it could be matching 10. Let's try 10. So 10 is being connected to 4, and 4 is being connected to nothing. So 4 is being connected to nothing. So what is F being connected to? F is being connected to B, and B is being connected to nothing. Wait, that doesn't line up. Okay, so the reason why, okay, that doesn't line up. Okay, I'll show you why it doesn't line up. So if we look here, we have 1, 2, 3, 4, and then they're being ended by no. So here we have 1, 2, 3, and not 4. So this is wrong. That leaves our option as B. That means B is the right answer, but let me show you how it could be the answer. So now let's look through the lens of B. Therefore, K. So we have to put K as here. And then F is down here. I hope that made sense to you, but I'll just go through more thorough proof that the answer is B. So if this is K, all this stuff is K. Okay, let's look through the options. So E, what is E connected to? E is connected to A, and A is connected to C, and C is connected to nothing. So nothing. G is connected to D, and D is connected to nothing. Nothing. J is connected to I. And then what is I connected to? I is connected to nothing. And now let's circle our activities. 1, 2, 3, 4. That perfectly lines up. There's 4. 4, 1, 2, 3, 4. And here 1, 2, 3, 4. And then there's 4 no's on top. And there's 4 no's on top. So E, G, H, J all correspond to 10, 3, 6, 7. So therefore the H would be corresponding to the 3. The 7 would be corresponding to the E. But yeah, it doesn't matter, whatever. You wouldn't have enough time to prove the whole thing. But just in case you guys are wondering, I did try putting it all in. And this is what I got. You guys can double check if this is the answer. It's really messy, but these are all the paths. And then you can go through the table and double check. Anyways, hope you guys are doing well. Do not fret if you got these questions wrong. They were a hard exam. Anyways, thank you guys for watching. Goodbye.